vectors, from our standpoint, I'll just say that vectors are not a line. It's not a line. As you can see, the way I'm showing it right here, it looks like a ray, but it's not a ray. In geometry, you guys learned, or may have learned, there's lines, line segments, and rays. So a line segment would look like this. That's a line segment. A line would look like this. Arrows on the end, goes on forever. And then a ray could go like that. But we're going to deal with vectors, so it kind of looks this way. Vector notation, if you can see this, P and Q, hard to tell from my graph, but there's like an arrow right here. Sometimes I tend to not even put that because it looks like a ray. It gets confusing. So oftentimes for me, I'll do like a half flag, a half arrow. So you know that it's not a ray, it's something different. So we're going to call it a vector. Vector, two things about a vector. It has a direction. So because I use the word direction, that implies that there is an angle that points the vector in a certain direction. Like this vector here, if that's a vector, then it's going to the southwest quadrant, starts here and heads southwest. So it's got a certain direction, so there's a direction angle. So there's still trigonometry that we'll be looking at. So the direction angle, and it's a line segment, so there's actually a distance. So even though that this doesn't look like a line segment, it actually is. There's a length of it. And it does stop right there at the point. So all this is doing, the arrow is telling you that it starts here, it ends there, so it's pointing in the southwest quadrant, not in the northeast quadrant. So vector is a directed line segment. If you've got 2 points, for instance, I probably have it on the next page anyway, but I'll just do a brief example. Let's say I have a point right here, and I have a point over here. And you have to say, well, which one's P and which one's Q? Makes a difference for vectors. Just because left to right, I'll call this one P and I'll call this one Q. Well, this is your initial point. P is always initial point for our textbook. That's the terminal. So you're going to go like this. So that vector has a length. The distance between these 2 points is found by a distance formula, which is down at the bottom. Here's the distance formula. And the distance formula in vector language is identified as these double bar. It's like double absolute value, which absolute value actually is distance too. I don't know if you've ever been told that. The absolute value of -3 is 3. Of course, we know that. But it's the distance that 3 is from the origin. Oh, okay. So the distance the distance that -3 is from the origin, it's 3 units. Distance is always positive. So some books might do this. A single bar, so it's like absolute value. It means the same thing as that. But I'm using the double bars to indicate something a little different, like vector language. It's called magnitude, by the way. We don't say absolute value necessarily. We'll call it magnitude. And it's a number. So magnitude is a number. Let's see right here. Magnitude is a number. Magnitude is a number. This little pointy thing right here, that notation indicates vector language as well. So you're going to learn two different ways of writing a vector in terms of notation. Trying to think of how I liken that. Two different ways. Oh, in statistics. I'll just say in statistics. Some of you have had it before. I don't know if that's a good illustration. How do you write it two different ways? Yeah, I don't want to use that. Well, okay, can't come up with it. Vector language, though, you're going to have two different ways. Here's one way. That's called a component form, vector component form. It's pointy brackets with a comma between A, B, whatever those are, or you're going to have what's called the IJ form. So you'd have AI plus BJ. That's another form. I believe our textbook that we use for calculus uses this form over that form. Our current textbook that we use, and when you do 1B in particular, it uses the IJ and even K form. If it's three-dimension vectors, you're going to have IJK. You'll be AI plus BJ plus CK. And it would be a triple, like 3 dimensions, vectors in 3 space. Okay, let's see what else I got here for an introduction. Okay, if I want to plot these 2 points, let's say these are standard points, X and Y. So let's plot these 2 points, -1, 2, so -1, 2. Okay, so we're going to identify that as P. P is the initial point, Q is the terminal point. So that's P, and then 3, -1. So that 1, 2, 3, -1. Now to draw that, I want to draw it from that. The next thing is I'm going to find what's called a vector V. So the vector variables for our textbook, vector variables are UVs and Ws. UVWs. Now they're just dummy variables. Like in algebra, when you solve equations in, say, 2 variables, you usually use X and Y. But if you solve 3 equations and 3 unknowns, equations of 3 variables, well, X, Y, and Z. But there's nothing special about them. You can have other variables. So for us, vector V is maybe V for vector, but I could use U's and W's as well in the textbook. Or capitalized M, N, and L's. Those could be vectors as well. So vector V is found to take the difference of the x's. So which one's first? This one? Well, okay. It makes a difference on who's first and who's second. P is first, so this is first. Q is second. So that means I got to go 2 minus, 3 minus a -1. So that's 3 minus a -1. And -1 subtract 2. -1 subtract 2. Vector V is 4, -3. And this is called my A, and this is called my B. A and B. And if I wanted to write this in A plus BI, AI plus BJ form, it would look like 4I minus 3J. Yeah, the I is not imaginary. We're not into imaginary sections right now. So what I want to do is plot or graph vector v instead of vector pq like this with the p's and the q's. Vector v, I'm going to do it as 4, -3. So anytime you're given a vector in component form like we have here, you always start at the origin. So instead of drawing it like this with 2 ordered pairs, this is saying always start at the origin. It's going to feel like a unit circle. Always start at the origin and then go out to 4, -3. So 4, 1, 2, 3, 4, -3. So that's 4, -3. So you always start at the, so you're going to reorient every single vector that's, and it'll tie it to the origin. And then it goes out to, well, in this case, 4, 3. That's an ordered pair, 4, 3, where vector v, which is what I'm ready to draw, looks like that. Now, the reason why I did this is because there's 2 things. One is vectors. Let's see, sometimes we call them equivalent. Vectors are the same, similar. I'll say equivalent. Equivalent is probably the better word. Vectors are equivalent. 2 vectors are equivalent if they have the same distance, so the same length, and they're pointed in the same direction. So they have the same direction angle. So basically the vectors have to be parallel. See, like this. So that looks parallel. Slopes are the same. But notice the length where my finger is right here, that's the same. So they are equivalent. I could take this vector and move it anywhere I want in the grid, like right here. That would just be a different P and Q. It'd be like R and S. But it has the same length and the same direction angle. So we say they're equivalent. Vectors can be multiplied by what we call a real number. They call it a scalar. And so here's vector v. You can see the shadow right here. If I went 2 times vector v, it just doubles the length. That's what it does. It doubles the length. So this is twice the length of that one. The direction's the same. This one here, the direction went 180 degrees. It flipped around compared to that one. See where the arrow is on your sheet? See, here's the arrow there. Here's the arrow here. So it flipped it around 180 degrees. So if I want to take this vector and multiply it by a scalar or a factor of 3, it's as if I multiply, like distributing, multiply the 3 to every component. That's the 7 and the 3. And you just got 3 times as long or as big for each one of the components. So the algebra vector scalar, pretty easy. Okay, let's see, what do I want to do here? I want to draw these 2 vectors for some reason. Okay, on the same one, let's see. Yeah, okay. This is X, oh no, actually this is A and B. If it's in vector component form, these are A's and B's instead of X's and Y's. Okay, so A is 1, B is -2. A is 1, B is -2. You go like this, and then you, and I have a red pen somewhere. Here it is. Now to draw this one, well, all I'm going to do is distribute. It's like distributing. So U is equal to pointing -2, +4. So the negative will cause it to change the direction. And so a -2, 4. So you go -2, 1, 2, 3, 4. Oh, yep, okay. See, so it's pointing in the opposite direction, and the red is twice as long as the blue. So this is vector v here, and this is vector u. Okay, you'll, let's see, you get a number that you can multiply to a vector. You're allowed to do that. You can also, algebra, you can add two vectors together. And I'll show you how to do it. It's like imaginary numbers. Can you multiply two imaginary numbers together? Yes, but can you multiply two vectors together? Not the way you would normally think, but you can add them the way you would think you could. Like these two right here. You can add those vectors together because all you're going to do is add the components. -1 and 5 is 4, and 2 and 1 is 3. So it's pretty simple. What it does, though, is if you've got a vector A here and a vector B here, not tied to the origin, just some P to Q and Q to S, let's say. Then when you add them together and you get a result, that's why they call it the resultant vector. It turns out it's the vector that connects the diagonal of a parallelogram. Whoa, that's a mouthful. Okay, so when you add two vectors, you actually create here the top half of a parallelogram, because if vectors are equivalent, then this vector right here is the same as this vector right there. It's the same direction angle because they're parallel, and the length is the same. And likewise right here. So then if you got a parallelogram, the result, which I'm going to show you here in a moment with this example, the vector that you get will end up being right there. It'll end up going right at the end. So instead of talking so much about it, I'll just show you. Okay, -1, -1, 2. I'll do A and B in blue, and then I'll do the resultant vector in red. So A, -1, and then 2. B is 5, 1. So 1, 2, 3, 4, 5, 1. Okay, so this is A, and this is B. And then when I do these together, vector C will be -1 plus 5. So -1 plus 5, comma, 2 plus 1. Vector C is equal to 4, 3. And now I'm going to take vector C in red and find 4, 3. There's 4. 1, 2, 3. And if you can envision that B could slide right up here and connect the, sometimes they call it the head and the tail. They'll connect these two endpoints right here. See, vector B. Here's vector B. I'll just do it in like a dotted. Here's vector B. And here's vector A. So it's a parallelogram. It just turns out that the resultant vector is in between. It'll never be outside. It's always the resultant vector is always contained inside the parallelogram. It's never going to be outside, never outside. Subtraction of vectors to demonstrate it. It's usually a little harder to see it or to understand what's happening with the picture. But the algebra, pretty easy. If I end up saying what's u subtract, subtract that from here. See the phrase subtracted from? It doesn't mean u minus v. It means you're going to take v and subtract u from it. So I got to go like this. Okay, and we're going to call that vector w. So let's see, vector v, if I go like this, 12, comma 2, and subtract 4, comma 5, vector w, then will be pointy, that would be 12 subtract 4, comma, and 2 subtract 5, 8, comma, negative 3. So pretty mechanical when it comes down to, hey, add and subtract vectors. Okay, we don't have multiplication of vectors the way you would think about what it would look like, hey, we'll do FOIL. Yeah, it don't work that way. Or division of vectors. We don't have anything like that. So just adding, subtracting vectors, and then taking a number and multiplying it to a vector. And it'll always give you vectors. What we will see in the 6.7 is what's called the dot product. The word product implies multiplication. So there is something multiplying stuff together, but the dot product of two vectors produces or yields a number, not a vector. Dot product produces not a vector. Vector, okay, so you got this representation. Sometimes they call it standard form of a vector. Pointy bracket, sometimes it'll look like the A or the IJ form of a vector, looks like that. We've already talked about that. Let's see. Okay, well, let's take a look at this. So vector U is equal to PQ with a half flag maybe, which would be, okay, let's see, Q minus P. So -4 minus 3, and then 5 subtract 7. You always take the Q and subtract the P pieces, which is equal to -7, -2, or -7i minus 2j. RS, so vector V maybe, would be RS and a number of examples. I'm not going to do them all. I think what I'll do is what's of interest is this one and this one. I'll do those two, because I think adding and subtracting, you get the idea, and taking -3 times those things, it's one step and you're done. Magnitude, I'm going to show you how to do the magnitude, but I'll do it with a bigger one here. So let's do this one here. That would be -3 times the U, so that'd be 4, 5. And then plus 2, pointy vector V is 12, 2. It's like distributing now, so I'm going to multiply -3 to both components. So -12, -15 plus 24, 4. Now I add the vectors together, and it looks like I get 12, -11, if I haven't made a careless mistake. Now, number 6 is just number 4, but taking what's called the magnitude. Now, the magnitude, it's about 4 pages before. Magnitude is taking the components, which we call A and B now. This is your A and that's your B. Taking the square root of those components squared and the sum of them. Okay, gosh, what does that say? You're taking the square root of the components, not those numbers right there. These components, taking the sum of the squares, and that would be A and B. So this is the distance, called the distance of that vector, the length of the vector, where if I looked at this being some vector, say W, that starts at the origin and ends at that ordered pair 12, -11, which is what, quadrant 4? So the length from the origin to quadrant 4 number is this number here that I'm wrapping up, 144, 265. Yeah, 265. And then if you can pull out a perfect square, you try doing that. It's a little bit of arithmetic or algebra after that.
Can you show for a couple more seconds? I'm on the last line, sorry.
Yes, no problem.
Okay, I'm good now. Thank you.
Again, another one that's similar, but it's in the IJ form. So I'm going to go 3I, 5J. Well, gosh, I can just, this almost feels like variables with parentheses. So I don't even have to have the parentheses here because you're going to end up collecting like terms. So the I's and the J's are going to go together. So I'm just going to distribute the -4. And then collect the I portions and the J portions. So -5I and then plus 17J. And finding the magnitude, which you could do this, magnitude of -5I plus 17J. All right, to find the magnitude, we go square root of -5 squared and 17 squared and take the sum of that. Ends in a 9. 17 times 17 ends in a 9. I don't have this one memorized. 289. 14. Yeah. Last thing that we'll look at in this section, it's called a unit vector. And like a unit circle, remember doing unit circles in trig? What does the unit imply? Anybody? What's unit circle? What does that imply? Unit circle. What do you think unit means? Anybody? Hope you know, because we did it in chapter 4. The unit circle, I think it was 4.2. All right, you guys are quiet today. It's a circle of radius 1, unit circle. Okay, so we did that. So there's got something to do with the number 1. A unit vector has a length of 1. The magnitude is 1 on a unit vector. Oh, all right. Well, let's see if these are unit vectors. I take the length of each one of this one here, magnitude, that's not going to be 1. This will be the square root of 9 plus 64. That's not 1. That's not a length of 1. So in order to get this vector to get shorter, you're going to divide by its magnitude. Oh, so I still need to find the magnitude of this vector. So magnitude of 3, -8. Square root 3 squared plus -8 squared. 9 and 64, 73. So a unit vector for this would have 3 comma -8 divided by, well, okay, I could make this as a fraction. You know, like here. so it'll feel like a scalar multiple. So I'll even show it to you that way. So 1 over V. Okay, here's V. I said it wrong. 1 over the magnitude. So 1 over square root of 73 times the vector V. So that would be 3 comma negative 8. So vector 3 over root 73 comma negative 8 over root 73. And that new vector has got the length of 1, basically, got the length of 1, where this one doesn't have the length of 1. Standard unit vectors, there's 4 standard unit vectors. The standard unit vector would be vectors that are sitting on the x-axis. That's tied to the origin, and they have length of 1. So it's from 0 to 1 and 0 to 1, 0 to negative 1. Those are called standard unit vectors. So it's I, j, negative I, negative j. Where's the I and j? So instead of A and B, this.
I do have a question.
Yes.
What is like the practical application of a unit vector?
Oh, well, if I had taken, I sat in on I forget professor's name. Anyway, I think it was a physics 40 class, sat in like a 2-hour lecture. That lecture answered a bunch of those, like your question. And I go, oh my gosh, look at what they're doing, the trig and the vector language they're doing. So I don't have an answer. I think if you went to a physics 40 instructor or something like that, they're going to tell you how, why, where, and not just vectors, but the unit vector, if in fact there's a practical application. Unit circles, I think we started that in trig by because it was simpler, and then we could take any circle of any radius, but we always tied it to the origin. That was so nice. So taking any vector that's with points, tying it to the origin is going to be very nice. And whether or not physics 40, as an example, we'll talk about it. So I'm avoiding the answer. I don't have an answer. I just do the math. Sorry. You can Google it. See what Google has to say. Yeah, that's all I would do is Google it. Our author may have a few word problems. Sometimes they'll talk about work and projection. And again, it's just a very simplified beginning physics type question that there's a force that's applied to something that's being linear pull. Okay.
Yeah, Google just kind of said the base answer was velocity measurements. So like feet per second, meters per second, stuff like that.
Unit, yeah, units per second. There you go. Mm-hmm. You know, when you get into 1B, it's been a while since I've taught 1B. When you get into 1B and you get into that whole chapter on vectors, there are applications, and there's a lot of physics applications that will probably discuss that as well. So there's another place that I just don't remember. Okay, so the last, thanks for the question, Morgan, by the way. Sorry, I didn't have a good answer. The last section on vectors is called the dot product. Now, for us, the dot product, what that does, it finds the angle it helps you find the angle between two vectors. So what practical application would that be? I think there's probably a lot of applications I can probably, if I understood what vectors were, then having the angle between, shoot, bearings. I could make a bearing problem, you know, a ship is in quadrant 1 and a ship is in quadrant 3, and you can come up with a bearing. What's the angle between them if you need to understand nautical stuff, I guess. So I can always create most things in our Cartesian or rectangular form, create them as vectors, and then we're doing the trig in this second half of the semester to find the angle between. There's other ways of doing that, by the way. Oh, now that I'm talking about it, I might as well go ahead and show you. Say a ship's over there. Let's say a ship's right here. And don't assume it's a 90-degree angle. It's just some angle that's acute. The angle between is acute angle. If you knew the position right here, because you knew how fast they were moving away from the harbor, and you knew the length of time, then you know that distance. You know that. And so you know whatever this distance, I don't call it R and call that D, you know that. And then if you had the bearing, which you can probably find pretty easily, then if you had the bearing, you can find out and know that that right angle appears, and then you could have this Y and this is X. So can you use trig, right angle trigonometry, to find this angle? Oh yeah, easy. That's what you've learned this whole semester, right angle trigonometry. And the same thing with here. You knew that. So this is a new X, let's call it, I don't know, W, and this is M or something like that. So can you find this angle and this angle with two triangles? Thumbs up. That's elementary for you guys today. What's different is to find that sum of those two angles, we can use something called dot product, and it'll find the entire angle. Find it. So I just got to show you the formula, what it involves. Okay, this is similar to the picture I drew, similar. If you want to find this angle, that's what we're trying to do, which is acute. Excuse me. Doesn't have to be acute, which turns out to be obtuse on this one, but it could be acute or obtuse. It'll always find the angle less than 180 degrees. The dot product will always find the angle that's less than 180 degrees, but more than 0. Here's the formula. Right there. So what you do is you take this thing called the dot product in the numerator, which is new. The bottom is just the magnitude of each of the vectors, so that's old for you. You can do that. And it's how to find the dot product. So here's the dot product formula up here. So we do something with the first components, but there's no FOIL. It's not like FOIL, nothing like that. And there's some addition thing going on as well. So we've got, let's see, these are just numbers. So this number times that number is here. This number times that number is here. You add the two numbers together. This is a number, not a vector. So dot product is not a vector. Adding vectors, vector. Dot product's not a vector. It's a number. Okay, and you can see an example that I did here. These two vectors. So I'm going to multiply and add, and you get the number 4, whatever that is. Right now, it's just a stupid number. When you take the stupid number and put it in the formula right here, it will help you find the angle. Remember how to get theta all by itself? Remember how to do that? How do you solve for theta? What's going to happen here? Anybody? How do you get the cosine off? Because that's what has to happen. Remember that? You should remember it. You're supposed to.
You inverse on the other side.
Right. So you take the cosine. It's like you take the word, pull it off, and you stick it on the other side, and it becomes a cosine inverse. So that's all it is. And you can see it down here. The nice thing using cosines is because you'll get angles from 0 to pi, or 0 to 180 degrees in quadrants 1 and 2. Now, why is that important? Because cosine inverse is defined for quadrant 1 and 2. Cosine is positive in quadrant 1, cosine is negative in quadrant 2. So that's where the cosine inverse. Rather than the sine inverse, that throws us in quadrant 1 and 4. So we just don't do with the sine, we do the cosine. Let's just draw the pictures. Okay, draw the picture. Negative 1, 2, 3, 4, 5, 6, and 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Five, 12, 1, 2, 3, 4, 5, 12, 11, 12. The angle looks acute. It just looks acute. We'll find out in a moment. Okay, now find the angle between them. That means I have cosine of theta, and this is right here. That's theta is equal to. So now the question is v dot u or u dot v. It doesn't make a difference, actually. See the formula over here. It says v dot u, but it could as well be u dot v. It'll give you the same thing. Think about it. This number times that is the same as that number times that. So it's commutative. Dot product is commutative. Okay, we'll do the v dot u because that's what you see in the formula. Magnitude of v, u. Okay, so v dot u. Okay, so we multiply these guys together. That's negative 6 times 5. And then you add the 10 and the 12. And then you take the square root, the product of the square roots. So what goes in here is the negative 6 squared and 10 squared. So that's 36 and 100 over for you. 25 and 144. So cosine theta. Negative 30. Oh, what is that? 120. $90? Yeah, 90. I'm going to stop simplifying there because the point isn't the simplification. The point is taking the cosine inverse. Yes, that's 13. I get that. You could make it 13. I'm just going to go theta equals cos inverse what you could do is take the product of those, because that's true. You could go square root of 136 times 169, because that's true. Anyway, I'm going to do this. Cos inverse fraction 90 square root. Oh, degree mode. I'm going to check. Always mode. Okay, good. Degree mode. Okay, hit enter. Shoot, something happened. Okay, 5, 5, 5. Oh, I have a division. Should
Yeah,
be
it's a
times.
division.
Yeah, it should be times in here. Okay, 53.6 degrees. 53.6 degrees. Okay, 2 decimals, Jess. Okay, 53.58 degrees. And this is just a summary of what I've done already for you. I wrote those down somewhere in your packet earlier today. One example says it all, because that's pretty much all you're going to be doing. I don't think I assigned any word problems. The only word problems would be, as I said, the projection / work problems. But yeah, I didn't assign any of those, so those won't be on the test. Yeah, I'm not going to do this. Like the last topic is this phrase orthogonal. Now, yes, in 1B, you will see the word orthogonal a lot. You'll also hear normal a lot, the normal vector. So we don't have that in this course, but anyway, it'll be defined for you when you get to 1B. The normal vector, and then vectors orthogonality, or I wonder if it's orthogonal. That's what you're going to check right now. Are the vectors orthogonal? So 2 things to see if they are, the dot product is 0. I'll say it again. If you took the dot product and you got the number 0, that tells you that the vectors are orthogonal. Now, what the heck does orthogonal mean? The angle between the 2 vectors, 90 degrees. If the angle between the 2 vectors is a right angle, then those 2 vectors are said to be orthogonal. Hopefully that makes sense. So, I mean, you'd have 2 vectors. If you have a vector that looks like that and a vector that looks like that, and you know for a fact that's right angled, then vector U and vector V, taking the dot product will produce the number 0. And if you produce the number 0 in this formula, see, if 0 is up here in the formula, 0 over anything non-zero is going to be 0. And then what's cosine inverse of 0? Some of you don't know. Okay. Cosine inverse. Okay, cosine of what angle is 0?
90 degrees.
That's supposed to be the answer. Let's see if that's true. Let's see. Do it this way. Yeah, 90 degrees. Okay, the last problems is basically, hey, is it orthogonal or not? All right, well, let's try this. V dot U equals 2 times 4 plus 8 times -1, which is 0. Yes, orthogonal. Yes. So if you graphed either one of them, it should look like that you've got a 90-degree angle. Should look like. Finally, this one, B dot U, 2 times -1 plus -2 times 1. Oh, it's not orthogonal. Okay.